So, in this lecture, we are going to cover some of the math preliminaries, which will be using, or the ideas of which are very useful in our course. So, let us see what we have to talk about. So, the first thing I wanted to highlight is what we mean when we are doing this operation y equals to ax, where of course this y and x are vectors. So x is in Rn, and A is also in n cross n matrix. Suppose this sort of an operation is happening, then what exactly is being done? So always try to get the picture in your head whenever you are doing maths. So try to understand the geometry, or the or try to understand how the picture is looking in some space. So you must have a clear idea, a clear view of that picture. So when you have that picture in your mind, you will understand math in a better way, and you will understand the significance of what we are doing when we are doing this sort of mathematical operation. Let us see. Having Suppose this n is 2, for the purpose of our ease of drawing. Suppose this n is 2, and suppose we have the vector x. This is the vector x. This is the vector x. This is like x1, x2. So this x is having some coordinate here. So maybe I have drawn it like very equal to each other. Suppose this is 3, 3. So my x is 3, 3. Now let me suppose that my A is some matrix, of course 2 cross 2 matrix. Maybe this is like this, I don't know. Turn up, let us assume this as the A matrix. So when we do this operation AX, then what we get is basically another vector. You can easily do this operation, minus plus 6. So this is plus 3. This would be 3 minus 3. I don't want a 0 right now. Change this. Suppose this is 1. 3 plus 3, which is a 6. So we got a 3, 6. So if this is of 3 length, then my x1 is still 3, but my x2 is now 6. So somewhere here I go. So my new vector will be this. So this is y. So what I have done is I have been able to go from a starting point, to another point by application or by operation of this matrix A. So if we want to go from one position in a vector space, so this is a two-dimensional vector space. So if we want to go from any particular position to any other position in a vector space, then there is a matrix. So it might not always be this particular A matrix, of course, but there is a matrix which, when operated upon this initial vector, suppose this is another vector, let me call this p, and this is another vector, let me call this q. So there would be some matrix, maybe another matrix A, or let's call this M. So some matrix will obviously always be there, so that MV will be equals to. So you by noting down v and u, you will be able to find out m. Also, if you know m, then you operate it on v, then will land up on. So this is what is going on when we are actually uh, operating vectors with matrices. So some more thing to get to note down is this, that if so here both these vectors, both the initial vector and the final vector, in this case x and y, in this case v and u, so all these vectors are still in R2. So they don't change the order, or they don't change the dimension of the vector space. So if the dimension of the vector space is not changed, then we can say that we are in the same vector space. So and this vector space in our case is clearly defined by these two orthogonal vectors x1 and x2. So these two orthogonal axes clearly define this vector space. What we mean by that? We mean that any vector, if you choose inside this vector space, that means any position in this vector space, can be denoted in terms of x1 and x2. So uh, there is some x1 component and some x2 component of any vector. So if I suppose this talk about this v vector, then it has a x1 component which would be equals to something, and x2 component which will be equals to something. Similarly, you would have a x1 component and a x2 component. So why we have only x1 and x2? Because the dimension of the vector space is two dimensional. So we know that a two-dimensional vector space is nothing but the plane. So this is the plane of this screen. And if we have a three-dimensional vector space, then one vector x3, an orthogonal which is orthogonal to x1 and x2, could come out of the plane of this from this origin. It could come out of the plane and perpendicularly, and that would make a three-dimensional vector space, and our vectors would be lying in those three-dimensional vector space. So then we would need another coordinate x3, another value here x3, in order to represent that vector completely, and those vectors will lie on the R3 vector space. So in general, any vector, in general, when you are talking about in general, this what we have down here, in general any vector can lie in an nth dimensional vector space, n-dimensional vector space. And if we operate that n-dimensional vector with a nth order matrix, then what we are doing, we are simply going from one point in that vector space to another point in that vector space. And how we are going, that is determined by what this particular A is, what exactly the elements in A are. So those elements will determine how we are going from the initial position to the final position. Let us look at a general matrix and a general vector and understand how this is happening. So suppose we have a three-dimensional vector x1, x2, x3, and a matrix like this: A11, A3, A21, A22, A23, A31, A32, A3. So when you operate this vector, any initial vector, this is any initial vector which is determined by this x1, x2, x3. So you would know the x1, x2, x3 values for that particular vector you are working with. You also know these A elements in the A matrix. This is the A matrix. So you know all these elements. So what is basically happening? You are scaling the x1 entry of the vector, the x1 coordinate of the vector with this element a11 of the matrix. Then you are scaling this x2 with the a12 element, x3 with the a13 element, adding them together in order to get the x1 coordinate of the final vector. So the final vector we are calling y. So we would write this as y1, y2, y3. So it is the first coordinate. So if I don't use the term x1, x2, x3, this is the coordinate number 1, this is the coordinate number 2, this is the coordinate number 3. So to get the first coordinate, coordinate 1 of the final vector, we are scaling the various coordinates. So all the three coordinates are getting scaled in general. In general, all these elements can be assumed to be non-zero. So each of the coordinates of the initial vector are getting scaled by something and then added together. So this is a11, x1, a12, x2, a13, x3. Similarly, this. So a matrix multiplication of a vector is nothing but a scaling and adding operation of the individual coordinates of a particular vector. So we apply a matrix to a vector, it is doing nothing but it is scaling the individual coordinates and adding them up. That's all. So in a diagrammatically what it is doing? Diagrammatically it is recognizing the position of a vector in a vector space. So like this vector space maybe, and it is recognizing the position of a particular vector in this vector space. It is recognizing the x1 and x2 and then utilizing this and scaling this in the direction of x1 as well as in the direction of x2. So I am restricting my diagrammatic representation to a two-dimensional case. So suppose my a11 is 1, a11 is suppose 2, then in the final vector, wherever from whichever vector I start, I get the x1 scaled by 2 times. So I reach to x1. Suppose my a12 is a12 is 3, then the x2 component gets scaled up by 3 times. So I reach somewhere like this. So I will this is 3x2 x2 this particular length. So I have to reach up to this particular point and I get the final vector like this. So this is what is happening. This is all that is happening. So if I want to move from one position to another position, this is what actually in control systems we want the state vector to do. The state vector is evolving with time. So it is actually changing its position in the vector space. So the state vector is changing its position in the vector space from one place to another it is going. So we want to understand or recognize how its movement is happening. So maybe we can say in another way that we in some way we are concerned with understanding what is that particular matrix which is making this possible. And also you have already seen something like the similarity transformation and the homogeneous system x dot homogeneous system is x dot equals to x. The similarity transformation will be like this, x equals to pz. So this sort of thing, what they're trying to say, you can figure out yourself now a bit. Try to think on this, and in the next lectures we will cover how what this thing actually means in terms of the diagrammatic representation, when we have the idea that what we are actually doing is nothing. So when we are actually operating a vector with a matrix, we are doing nothing but changing the position of the vector, or we can say another way, we are scaling that vector in all the coordinate directions. We are scaling that particular vector in all the coordinate directions. In this direction we have scaled, in this direction we have scaled. So in all the independent coordinate directions we are scaling that vector, and hence thereby we are getting a new vector. So that scaling idea, let us simply understand the scaling actually. So when we scale a vector by a scalar, then when we have a scalar scaling a vector, not a matrix, okay, simply a scalar scaling a vector. So I have some alpha x1 x2. So maybe this alpha is free and my initial positions are 1 2. So what I get is basically 3 6. So the scaling of the vector in diagrammatic representation will be like this. So you have 1 x2 and this vector 1 2, so something like 1, then might be 2. So this is the vector, and the scaling is what is happening, this is becoming 3. So I'm scaling both sides by 3 times. So maybe here. So the new vector is basically nothing but this getting extended, and you see that the new vector or the resultant vector is in the same direction as the initial vector. So it's like this vector is getting elongated by some amount, and what is that amount by which it is getting elongated? Nothing but 3. So the length of the final vector, so suppose I denote length by L, length of a vector by L. L is, in this particular case, L is x1 square plus x2 square by 2, I think, by 2. So then your L1 L2 is 3 L1 in this particular. So scaling is this sort of an operation, and when you are using a matrix, then what you are doing, then you are scaling all the coordinates and combining that result in order to get one of the coordinates only. So if you want to get y1, you are doing a scaling of all the coordinates. So some scaling is here, some scaling is there. You are doing a scaling of all the coordinates and then combining them together to get the one of the coordinates of the resultant vector. Similarly, y2 will also be a scaling like this. Okay, so this is what you are basically doing when you are multiplying a vector with a matrix. So get this idea in your head, and with this idea we will try to see what the many different aspects of control systems, because now we are dealing with matrices and vectors basically when we are in the state space realizations. So what they are actually telling us, so we would be able to dig into those um, symbolic representations of x, a, y, x dot, what these things are actually giving us in a diagrammatic representation. So we'd be able to understand those things. So with this, I conclude this particular lecture. We would move ahead and explore the mathematics a bit more, and that will help us. That will give us the power to really understand how a control system in a state space relation behaves, and how we can actually analyze and design the control systems using this sort of representation. Thank you for your attention.